Welcome back to the second section where we're looking into the mathematical formulations of distance decay. In the previous one we were regressing so we can have the beta values, which we see there, the beta coefficient, which turns out to be a very, very small number given the restrictions we've got in the columns A to F. And we also retrieved a negative power function value, which is here expressed as a beta, but could just as well be called a gamma value, which is 1.315. So it's a little bit of a difference. So these are regressed values that could be used in any kind of model. There's also a possibility for us to work with a mathematically formulated one. And to do so, I need to go to another tab. So in here, we could look at the sort of the definition of how we define a beta value for the negative exponential function using mathematics, and the general idea of using it, this kind of a value, is one of the half-life models for carbon-14, in fact, so a quite different field. In the classic carbon-14 model, they were looking into the time it takes for some radioactive decay to reach its sort of when it's complete, and you can use that kind of a curvature to understand the age of any dead material or organic matter. In this case, if you sum up all the radioactivity, at some point, at some time, at some range, in all these kinds of millions of years sometimes, you have a position where you have got the half-life. So half of the radioactivity remains, and the first half has just been, and that distance in time could be expressed as a median. And if you sort of use that idea into commuting, you could say that the median commuting distance is also where the distance is, where you've got half of the population commuting up until this point, and the remaining half is actually commuting longer. So the same kind of idea works also if you think, at least, that there is a negative exponential sort of form to the distance decaying commuting. And much of it suggests it is, because an exponential function is very common to use when you're depicting commuting behavior. However, since we are dealing with commuting on a national level, it might not be the best, but that's another kind of an issue. So, how do we then create it mathematically? Well, the formulation is really, really simple. In this one, you could see here that you've got the log of 0.5, and 0.5 here represent the median value. So if you want to have the first quartile of 4, you would write 0.25. And then you would instead replace the median value with a quarter value of distance, where the first quarter of the population commutes. In this case, we have log 0.5 divided by the median distance, and we can make up any kind of value to understand what that is. In this case, I've used the value of 15, and the reason that 15 could be kilometers, it could be minutes, could be anything. That means that half of the population would then commute and up until 15 minutes or units or whatever, and the other one would follow on afterwards. The thing is that it's very simple to show what this looks like by doing this kind of a yellow long list of various kinds of distances. So imagine that we've got the full array of everything just on a line, and all the jobs are just pooling up on a long line with 1 units different as we go on. And we just got one job opportunity at each of these locations, so we don't even have to treat the jobs. They're just in there because opportunities time this function of this one, exponential function, is equals to opportunity times exponential function of distance and negative beta. But if you only have one opportunity, you can just dismiss that, and that's what we're going to do here. So if we go for the exponential function, we can see it is the exponential function of the distance, which is 5 in this case, times the negative the beta value, which is expressed up there. So you've got something that could be understood as a probability. At a distance of 5, you've got 0.79 probability, and then it just decreases. And the interesting thing is, and this just works for the exponential functions, by the way, but nevertheless, if you've got a half-life, it also means that the 0.5 probability is shown at the same distance. The half probability of commuting at a specific distance is not the same as a half-life, but in this very unique case when it comes to the exponential function. So that's kind of a fun side effect of these math. if we want to, we can in fact just express how the curvature looks by selecting a few of the first ones here and doing insert and line, and we could see a slow and gentle sort of slope to the exponential function, expressing the probability of choosing an alternative at the specific distance in question. So mathematically we can derive exponential functions. We can't do it with the power function, however, so I'm using the gamma value from the regressions, or any kind of value. You can see people using things like 2 or any 1.8, 1.5, where they're usually values that comes with statistics packages or known units of distances. So in this case, we just look for the specification of actually computing it. So we've got the power function equals the opportunity times the log distance to the power of a negative gamma. So the opportunity times the log distance. So in this one, what we do is taking the natural log of the distance times the to the power of the negative gamma value, and that expresses sort of a different kinds of value structure, but nevertheless. If we put these two on display, thinking of them as expressing a probability of computing over specific distances, whatever that unit might be, it looks pretty much like this, where you can see that the exponential function has got greater values in the beginning, but the power values have got a longer tail. So it's really got to do with how you think, what kinds of assumptions you've got in terms of how commuting is looking in the regional context, and what kind of commuting you've got. So see this as a probability, and I think you could realize that very, very long distances are going to continue for the power values, indicating there will be a fairly high likelihood of accepting also very, very long distances, which might be more common for migration than it is for commuting. But these kinds of things is yet to us to determine. So this is the mathematical specification of the decaying model, which means that we got now 3 different values. And the third value in this case is because we in fact do have not only a mock makeup value of the exponential function, we do know the observed median commuting distance for the Swedish population. And the median distance for the 2008 population is 6,010 meters, which means that it's easy for us to just sort of replace that value with this one, and having something that is 0.00012, representing the beta value that we're going to use in the models from here on. And therefore I am going to paste that value as that. So we got 2 regressed values, there you go, and 1 mathematically formulated one that we should use in the models. So in the next phase we're going to use these to actually express job accessibility, but that will be for the third part of the accessibility modeling. Thank you so far.